In this lesson, we talk about spread spectrum communication, and we do a brief introduction. And in this introduction, we want to say that the signal transmitted by a narrowband digital communication system is often susceptible to jamming and may be detected by an eavesdropper. So in spread spectrum, such information carrying data signal gets spread over a wider range of frequency using either direct sequence or frequency hopping spread spectrum techniques, and the such spread spectrum becomes quite efficient in a multi-user environment, and that is able to happen without getting interference from other users. And the CDMA is one of the examples that utilizes spread spectrum, and it is quite often used in cellular communication. So this is the example of the spread spectrum that and how it relates to the normal signal. So as a normal signal may require a frequency of bandwidth BW. We can call it BW. But on the other hand, we may spread the bandwidth of this signal to occupy this BW2. And therefore, you can see that the information signal bandwidth is far much less than the bandwidth 2 of that we have attained after we have done the spreading. So by definition, spread spectrum is a transmission technique in which the transmitted signal occupies a larger bandwidth. The keyword is larger bandwidth compared or than it is required. So as we have seen in this diagram, we are seeing that the BW1 is the minimum bandwidth required for transmission of this signal. But when we extend our bandwidth to occupy BW2, that means we are using more bandwidth than is required. We say further that the bitrate of the spreading sequence is much higher than that of the input data. We talk about spreading sequence later. So that suffices to say that the bitrate, which is also often called the chip rate of the spreading sequence, is way higher than that of the input data. The spreading of narrow bandwidth of baseband signal is normally accomplished through the use of spreading code, or what we are referring to as the spreading sequence, that is often considered to be random but pseudo. So it is called pseudo-random noise. It is random because it appears to be random, but in actual sense it is not random. So these are two contrasting words that talk about the characteristic of the pseudo noise. It appears to be random. It appears like it meets all the standards of any random signal, but when you observe it, you realize that it is not really random. It is deterministic. The opposite of random is deterministic. So we say that the PN code is always independent of the baseband signal. So they are never depending on each other. We can have a random or PN code, and we generate the baseband signal independent of each other, and this same code is used. That is another keyword that we want to underline, that this spreading code or the spreading sequence is used at the demodulator or at the receiver to decode the received data, and therefore the original baseband signal is recovered. So this is the general structure of a spread spectrum, in which case we have binary data arriving here, BT, and then it goes through a data encoder. The data encoder is the one that is producing for us the baseband signal, and then when we have received the baseband signal, we use a random noise code which is generated by some algorithm. This spreading code is just a sequence of ones and zeros, and it is normally dependent on the number of shift registers that are there. We look at that in more details later. So this spread code is modulated by the baseband signal to generate now a spread spectrum modulated signal, which now is sent to the wireless channel. And now if we have an eavesdropper here or a jamming signal here, as much as we want to detect or to jam our signal so that you are not able to communicate with the intended receiver, they will see a signal that appears with a very huge bandwidth. They are not able to know what is the spectrum of our message signal. Then at the receiver, we apply the same pseudocode, PN noise or code that are running the same algorithm, and they have the same seed, which we talk about at a later stage. These are the two factors that are required for the generator to generate the same code, irrespective of the location. Therefore, this is called the spreading code, and when it is multiplied or used to demodulate our spread spectrum signal, we are able to recover our original baseband signal. You see the details of that in our subsequent slides. And this band signal is now decoded to get our original data that was transmitted. So we briefly talk about the generation of the pseudorandom noise or pseudorandom sequence. And here you have a brief diagram that illustrates a typical generation of spreading code, where we have shift registers here, S1 to all the way to SM, and the output of these shift registers, which are sometimes called flip-flops or FF, are fed into the logical circuit, which sometimes is considered to be modulo 2 adders, and a modulo 2 adder is sometimes considered to be equivalent to XOR. If you remember your digital electronics, you remember that there are digital logic circuits that both perform logic operations on binary zeros and ones. And you look at the example, this is just the general diagram that we are getting some feedback, and the feedback is sent back to as input to the shift register, and by that way we are able to get some output sequence at the last flip-flop or at the last shift register, so that that is what produces for us the spreading code. So following that diagram, we can generally look at what is that we have seen the S1, S2 to all the way to SM, and what we see in the generation is that a clock signal is applied to all the flip-flops S1 to SM, and this clock is used to change the state of each flip-flop. There is some digital electronics here, but it is assumed that you are quite conversant with what we're talking about. So they are fed by the same clock signal. That is the keyword. And then the logic circuit computes the specified function, which is now considered to be the algorithm of our spreading code generator. The output is of this logic function is fed back as the input to the first flip-flop, and the feedback shift register is said to be linear when it is consists of logic circuits that are able to generate a modulo 2 addition. So for the M number of flip-flops, the output of the logic circuit uniquely determines the subsequent sequence of states of the flip-flop. So this logic circuit, we are talking about, we are getting some data. We look at that quite in detail in the next few slides. We are able to know that the number of bits in the spreading code is often given by 2 to the power m. So if you have, say, three shift registers, we are able to get 2 to the power 3, and therefore we are able to get a combination of zeros and ones adding up to 8. So we see now that the M flip-flop in a shift register always gives the required PN sequence. So this is the sequence that we need, and it's dependent, as you have seen, on the number of registers that are used. So 2 to the power m is the number of bits that actually is 2 to the power m minus 1. So 2 to the power m minus 1, the number of bits that are obtained when we have m number of registers. And therefore we will have this number of, call this m, we are going to have this number of clock cycles before the code that is generated starts repeating itself. So this here is an example of a linear shift feedback shift register, as it's same as they called. One model is that this one has how many? This is our first one, S1, S2, S3, S4, and S5. So this has m is equals to 5, and therefore 2 to the power 5 is equals to that 2. So we will have minus 1. So we will have 31 PN code, that 1 bit PN code. So we have a combination of ones and zeros that are not repeating, but after that 1 bit, we are going to see the code repeating. So in this case, the algorithm here is very simple. It's combining the output of register S2 and that of S3, and this is the XOR gate. At whatever is output from these two is fed in as input to S1, and that story continues. So that is one example of linear feedback shift register. And another one here is that of this one again has 5. In this model, the last bit S4 is considered to be the input, and the first bit S0 is considered to be the output. So in this model, the PM sequence is obtained from S0, and the input is considered to be going to S4. So, and again, the algorithm here that we have is quite simple. It's combining the output of S1. This considering the output of S1 and that of S3, ORed by this logic circuit, and the output of those two is fed into S4, and the cycle generates. So we look at a detailed example on how that happens. So I want to give an example of a design that we are going to use for our example. Consider this to be our S3. So this is C2. This is our flip-flop C1 or shift register C1, and finally we have shift register C0. And in this model, we are going to combine the signal is flowing this direction, and the output is obtained out of this. So this is where we are getting our PN sequence. So, and the feedback is obtained from as the linear combination or XOR of C0 and C1. And when we get this linear combination, we are feeding it back to our C3. So we always consider, and so this is what we are calling modulo 2 addition, and this is what we refer to as the feedback, and we have already indicated the input. So for a given number of M symbols or M shift registers, that is small m, we say that we need a starting code, which is also called the seed, and the only condition that we must never have this condition is that the starting code must never be all zeros. For us to be able to do any XOR or modulo 2 condition, we require that the seed must never be equal 0, 0. But we can have any combination of ones since we have ones anywhere. So for us, we can start with 1, 0, 0 as our starting code. Therefore, we say that this is 1, this is 0, this is 0, this is 0. Like if we are talking about flip-flops, they are initialized to this state. So we will now see what happens. For instance, when we say 0 XOR 0 is taken as the output. So 0, we know 0 XOR 0 is equals to 0. So our first 0 will come there. But then they're called shift register. So our next cycle will have 1 come here, this 0 comes there, and the next one will come here as 0, and the next one will come here as that. And now our new digit that we have obtained is this 0 that we have received from here, which is 0. And then we evaluate the 0 XOR 0 is what. So I will look at the scenario in the next few slides. So in that example that I have just drawn, we have started with 1, 0, 0, 0. So what we have seen after we are talking about this is what we are doing XOR combination, and therefore whatever is, so these two are going to be the output. This XOR this is going to be the input to our C3. Then we have seen this is going to be 0, and everything else comes shifted by 1 bit. So again, 0, 0 becomes 0 here. Then we shift the top one by 1 bit. Again, now we have 1, 0 XOR. This becomes 1. Then we move this other here. So 0, 0, 1. We are saying this is coming there. We're just shifting it by 1 bit. So without any contradiction or confusion, we are simply shifting 1 bit, and then we are considering these two XOR. Once we have XORed them, we find our value for here. And again, we know that 0 XOR 1 is 1. So again, we follow the same idea. 1, 0, 0. So we have zeros again. This 0 comes here. 0, 1, 1, 0. So I can complete the others. We continue with the sequence as follows. At 12 we have 1, 1, 1. At 15 we have 0, 0, 0, 1. And if we have 16 we repeat again to the way we started, that is at 1, 0, 0, 0, and that is where we started. So this, what is received at the output of the C0, not at C3. We have seen C3 is our input. So our output is the one that is picked from C0. These are the last 7 bits, and these are the first 7 bits. So that marks the end of the generation of PN sequence, and we get our PN sequence as follows. PN code is given by 0001101010111. So this is our 15-bit PN sequence, and it meets most of the randomness characteristics, and we'll see how we are going to use this code for our spread spectrum modulation.